Uh, Thank you for the invitation, and sorry I couldn't make it. Had some trouble with my passport. But okay, so I'm going to tell you about our journey to find the edge of the chart of nuclides. Uh, Before I get into that, let's just say a little bit about experiment here. It's the only experimental slide I have. So all the data I'm going to show you are a result of invariant mass spectroscopy. And it's all done at the National Superconducting Cyclotron Laboratory. And this device here I'm showing is HIRA, where we do most of the data I'm showing you comes from. So invariant mass, of course, you need to detect all the decay products. And we're looking at up to 6 decay products in some cases. And so you need the angle. So these are silicon strip detectors to give the angles of the particles, silicon cesium iodide to get PID, and the cesium iodide gives us the energy. When we go to the heaviest cases, the heavy core usually goes down the beam pipe. So we switch, and so we don't have very good efficiency. So we switch to a different mode where now, and this is the case of making magnesium 18, I'll show you, we actually detect the heavy core around 0 degrees with the S800 spectrometer. And then we have another array of silicon cesium iodides to get the lighter fragments. So, so this is the region of the chart of nuclides where I'm interested in, and the talk is focused. So the solid yellow, and I guess these blue are all particle stable, and all these boxes beyond that are resonances beyond the proton drip line. So we're interested in moving this way, away to the proton-rich side of the proton drip line, and interested in seeing how the structure changes due to the effects of the continuum. And one of the questions is, how far can you go before you reach the edge? Where is the edge? And that is, in the end, will be something sort of a diffuse border. But you know, as you go further beyond the trip line, the lifetime or the widths of these resonances, they just increase, and eventually these widths, these resonances dissolve into the continuum. And that is essentially the end. That is the point at which you can no longer consider to have a resonance. So, so what sort of widths are we talking about right at the edge? I noticed in high energy physics, they have some really large widths, like the W boson has a decay width of 2 GeV. But such a width is really totally unrisky for a nucleus. The time scales involved in those high energy collisions are much, much shorter than ours. So, I think the maximum width should be related to some of the time scales in the reaction and in the structure. So one time scale you can think of is that, you know, if you have a reaction that creates maybe some particles in a resonance in a direct manner, then the resonance lives for some time and decays. So that scenario becomes difficult to understand once the lifetime of the resonance is the same as the reaction time, and then it's as if all the particles were created in the reaction. So what would be a typical reaction time? Well, I just said how long it takes a projectile to travel one target diameter, for instance, and I put in some numbers here, like 100 MeV per nucleon projectile. You could pick some other number, some target diameter. Maybe you want it smaller for lighter nuclei, bigger for heavy, you know. But this would be a sort of a time scale for those direct reactions then. And if you treat that, say that's the maximum lifetime, what would then be the maximum width? You'd come out with something like 9 MeV. Another way you could think about that is you could say, well, you know, in a classical resonator, you would, to call it a resonator, you would like it to say complete a couple of cycles before it decayed. So what is the sort of typical time scale associated with an excited state or a state? Well, I'm not sure exactly in all cases, but one would imagine it would be something like how long it would take a valence nucleon to travel from one side of the nucleus to the other. So it's sitting in the mean field. So I'm saying it's like 40 MeV above the mean field. You can pick some different numbers if you like. Gain a target diameter, but I get a similar number for the maximum width. So this is kind of the maximum width maybe we can think about.
Bob, in the spirit of this meeting, I would claim that you have to divide this gamma by 2, because in order to get shell structure, you need to get a periodic orbit. So you'd like to go across the nucleus and come back.
Okay, well, as I said, it's you can put your own numbers in there, and I think it's the roughly the order of this is that's important. As you'll see, the lifetimes or the widths of nuclei increase very rapidly. So factor 2 might not make too much difference. Whether, let's say 6 MeV, take that, whether we could actually see a 6 MeV width. We had some talks today which talked about 3 MeV widths, so they're pushing this. I'll say it can be difficult, especially if there's high density states. If they're all 6 MeV wide, that would produce some smooth background. Can we discriminate this from a non-resonant background? And even if you have a single state, if your background has some structure, maybe it's also difficult. So even getting to this limit may be difficult. So I just want to start out close to the drift line and move out. So just below the proton drip line, we have 1 proton and 2 proton emitters. So you know the proton drip line is this black line here, and it moves backwards and forwards. Okay, and that's of course due to the pairing effect. Even Z's are more bound, and so the drip line sticks out further in the proton-rich region. And you see that all the 2 proton emitters, even Z, and all the 1 proton emitters are odd Z's. So those are the green and the yellow. And of course, like this magnesium 19, it can't be a 1 proton emitter because it emits 1 proton. It's still beyond the proton drip line, so it has to emit 2. So basically, wherever you start, you just emit protons till you hit red. And we've done a lot of work on this. I won't say too much about the 1 and 2 proton emitters because I want to get further out. For instance, a 2 proton emitter we recently made is oxygen 12. So this is the invariant mass spectrum. So this is 2 protons plus carbon 10. We created oxygen 12 with the oxygen 13 beam, knocked out a neutron. So from the invariant mass, we get what we call the decay energy. This is the invariant mass minus the mass of the rest mass of the fragment. So this would be the decay energy of an oxygen 12 state. And you see a nice peak for the ground state, and we have some excited 2+ states, and maybe even another state here. I note compared to the heavy 2 proton emitters, there were some talks about, we get a lot of statistics. So that's one of the advantages of working in these light systems, a lot of statistics. So we can look at correlations, and Vitek had talked about the correlations and how they're sensitive to both the initial structure and the final state interactions. But I won't go too much more on that. If we knock out 1 more neutron from the oxygen 13 beam, we make oxygen 11, which was an exciting, because it was the mirror of this iconic 2 neutron halo system, lithium 11. And there was a little background subtraction, but let's concentrate. So this is the final spectrum. This also points to our problem of finding resonances. So do we have 1 peak or many peaks? So this would be like 4 MeV wide, and that seems very wide getting towards the maximum possible. The decomposition I showed here is based on Gamow shell model, a couple of channels, sorry, calculations, Simon, Wang and company. And so they predict 4 states in this region, and there was some adjustment to the model based on experiment to get the best fit, but this is what we see. So we have like 4 whitish states here. And this is also, you know, the difference between oxygen 12 and oxygen 11. Now we're in odd even with oxygen 11. So we have somewhat a higher level density. And so the overlap, the white states make it even harder. There was a lot of interesting effects and structure due to the continuum here, especially associated with a virtual light state in carbon 10 proton, carbon 9 resonance. But we'll miss that. And the other thing I want to mention is, as well as measuring variant masses and stuff like that, we've also looked at cross sections. And I show here this well-known plot from Alexander Garter and Jeff Tosteven, where this is usually the bound state inclusive single nucleon cross section. So this is where you knock out either to a bound state or maybe some excite states, the gamma decay to the ground state. So this is the total yield from that, and they divide it by a theoretical thing, which is based on a iconal model for the single particle knockout cross sections times the standard shell model spectroscopic factor, and you get this rapid change as the difference in the neutron and proton separation energies change. So what I put in here in these red points are, these are exclusive now. So these are neutron knockouts to resonance states, to the ground states. So to neon 16, oxygen 12, carbonate. So that's these guys. And you see they don't seem to fall on the systematics. They seem to fall below. So I guess there could be a number of possible reasons, but we suggested that this was a result of using the standard shell model, because it doesn't include the continuum, and these are all in the continuum. And so maybe spectroscopic factors load when you knock out continuum to the continuum, at least in these specific cases. And there has been support, especially in this paper by Josh Wiley and company, where they did calculations for oxygen 13 and carbon 9 knockout and get similar changes in spectroscopic factors. But I wish to now move further out. So what happens as you go further out? Well, for instance, in the sodiums, these 2 green points here beyond the proton triple ion, of course, just single proton decay. But once you go to here, this point, this box here, you obviously can't single proton decay. So you go down to the red box. So that's a 3 proton decay. So for odd Z nuclei, you expect this transition from 1 proton decays to 3 proton emitters. And there are actually 4 known. One is off scale, potassium 31. But here are three proton emitters. And both of these we found actually through charge exchange reaction. So this is with the O13 charge exchange, this is with the neon 17 beam. So that seems to be an interesting way of doing it. And I'll just show you the data from one of these. So this is fluorine 13. So it decays to 3 protons and carbon 10. So that's the same as oxygen 12, but an extra proton. And so this is the decay energy distribution we obtain. And you see it's like 10 ME wide. So it's too wide to be considered a resonance. So there's some large background here, which we don't really understand. Maybe it's some sort of non-resonant background. Maybe there's contributions from very wide states overlapping. But you see, whatever it is, you see that there's some nice peak structure sitting on this background. So that's the state we're interested in. And this is a fit with bright Wigner line shape with experimental resolution included. So we have a peak here, which was 1 MeV wide after taking out the experimental resolution. What peak is this? So there was predictions from Terry Fortune and Raymond Scher, and there was like the 1/2 plus, and they had 2 estimations of an excited state, 5/2 plus. So it seems to lie directly for the 5/2 plus. So we believe this is the excited state. And the 1/2 plus we do not see. So either it's very wide, part of the background, or it wasn't excited. Grisha talked about, I think, the mirror of this in boron 13, and there was also discussion of a 1/2 minus, which would be somewhere down here, but we would also not see that. So in this case, we just see the excited state. So that's what happens to odd Z's. So what about the even Z's? Well, pretty clearly they go from 2 proton emitters when you go past the triple line to 4 proton emitters. And there are now just 2 cases of 4 proton emitters known. Carbonate has been known for a while, and quite recently we did an experiment with a Chinese group in Peking and found magnesium 18. Okay, so I'll show you some data from both of those. So this is the concentrate on this bottom slide. So we made carbonate from a carbon 9 beam, knock out a neutron. It 4 proton decays to an alpha. So we calculate the invariant mass, and as I said, it had been discovered previously. So using the previous mass, we calculated the excitation energy, and this is the spectrum we get, and we get a peak centered pretty close to 0 excitation energy. So our actually mass will be a little different from the previous study, and it's a reasonably narrow peak. It's actually taking out the experimental resolution, it's about 130 keV, which I think is the number Champey quoted. So what we did do is figure out how it decayed. And so you could ask, so this is carbonate, this is 4p and alpha, and these some intermediate things. Does it undergo a direct 4 proton decay? So a lot of the 2 proton emitters we see, just about all of them undergo prompt 2 proton decay. So is this a 4 proton decay, or could there be some sort of sequential type feature of the decay? And if you're looking for something sequential, you really need to have some narrow intermediate state in which to pass through. And the only narrow one would be this beryllium-6 ground state. So 2 proton decay to beryllium-6 ground state. So we can look for this beryllium-6 because it decays to 2 protons and alphas. So 2 of the 4 protons, if the decay went through this path, would be from the decay of beryllium-6. Well, there are 6 ways of subdividing the 4 protons we measured into just 2. So one of these 6 could possibly be the correct beryllium-6, but even if there's just one beryllium-6, the other 5 are incorrectly assigned to the alpha, at least for the process of making a beryllium-6. So we did the invariant mass of all of these, and now this is the beryllium-6 excitation energy. And you see we get a nice peak at 0 MeV, which corresponds to the beryllium-6 ground state. And then we get this broad distribution that's associated with the incorrectly assigned protons to the alpha. And as I said, there's only one of the 6 should be correct. So the ratio of this to the background should be 1:5 if there's one beryllium-6 in the decay. And I'll just say we went to some trouble to constrain this. So we decided to measure the line shape of beryllium-6, including the experimental resolution, by taking a beryllium-7 beam, knocking out a neutron. It's the same beam energy, same target, same apparatus. We looked at 2p plus alpha events. There's a beryllium-6 ground state. So we know the line shape with the experimental resonance very well. So we use that to constrain this fit here, which has the background and the peak. And the ratio of errors of this to the background is 1:5 within a couple of percent. So that says this decays through the beryllium-6. So I'll just show that again. So the decay here is carbonate, 2p decay to beryllium-6, 2p decay. And these two decays are very similar, 0 plus to 0 plus, almost the same decay energy. The intermediate states are wide and they're the same spin. Quite similar. Yeah, so Champey talked about excited states in carbonates. So we don't see any evidence in this reaction where we knock out a neutron. So we decided to look with our oxygen 13 beam. This is the same data where we found the oxygen 12 and oxygen 11. So to make carbonate, you would have to knock out 5 nucleons, 2 protons, and 3 alphas. So we can again look at the 4p plus alpha exit channel. And the histogram is what we got. I will say, though, that there was a background subtraction reasonably substantial here, which I won't go into, but we can make, we make an oxygen 12 state that decays by 4 protons and 2 alphas. If we don't detect one of the alphas, we will get a 4 proton plus alpha. So we can take these detected events and try and determine what the spectrum of the events where we miss one alpha. So we've subtracted those. And you see, so there's a nice ground state peak, which we saw before. And now on some broad background, there seems to be some broad state here. And also based on this idea here, we could also wonder, does the 2 plus decay through the beryllium-6? So we could basically gate on having a beryllium-6 in the decay. And that is useful because this oxygen 12 state doesn't decay so much for beryllium-6 ground state. So the background subtraction is much less. But anyway, this is the spectrum we get. And both spectrums show a broad peak around here. So Champey said his 2 plus state was 3.5 MeV above, or I guess excitation energy, so 3.5 MeV above the ground state, which is here. So that certainly puts it here. So I guess we're seeing the same thing. We seem to have a nice minimum between the ground state and the 2 plus. I imagine that's probably just from the different experimental resolutions. Anyway, we didn't know about Champey's results. So at this point, we asked our theoretical colleagues. So GTEX group, Josh Wiley, I want to ask them, where would the 2 plus state be? So this is their prediction. And it's, so this is gamma shell model prediction. Now they couldn't deal with 4 protons in the continuum, so they did a calculation with 2 protons plus beryllium-6. So anyway, it's a little high, but it's about the right position. So it gives us a good feeling. This is the 2 plus state. Their width is, prediction is 1.5. I think our data is wide. I haven't actually fit it. Champey said it was around 3 MeV, and maybe that's possible, depending exactly on the experimental resolution. What about the other 4p decay? So that's magnesium 19. This is quite recent. So we had to build a new detector for this, and we collaborated with a group from Peking University, and they took the data home and analyzed it. So this was a thesis of Yu Ying, a student in that group. Anyway, so magnesium 18, it's formed by 2 neutron knockout from a magnesium 19 beam at, I think, about 100 MeV per nucleon. So this is the 4p plus oxygen 14 invariant mass spectrum. And there's a nice peak here associated with the ground state. And Possibly there's a second peak here associated with the 2+ state. This is a rather clean discovery of the ground state. It's about 100 keV wide as well. So how does it decay? So again, you can consider some sort of prompt or sequential process. And you again look at the sub-events. So here I've looked at actually a number of different sub-events. Look at proton plus oxygen 14, 2 proton plus oxygen 14, 3, and proton. You notice if it was a 4 proton decay, then remember in 2 proton decay, the 2 protons come out in equal energy approximately, as that maximizes the product of the barrier penetration factors. So in 4 proton decay, if it was prompt, you might expect them to come out with equal energies as well. So the peak in that case would be at the total decay energy from the ground state divided by 4, which would be here. And we don't see a peak here. It's more like a little valley between 2 peaks. So it doesn't appear to be prompt for proton decay. We did a simulation, again, assuming 2 steps of prompt to proton decay, this time passing through a neon 16 intermediate state. And that's these red curves here. And this is the invariant mass of neon 16. And this background from the incorrectly assigned protons under that. And it fits the data quite well. So this is quite similar to the carbonate. So magnesium 19, 2 proton decays to neon 16, which is a known 2 proton decay emitter, and it 2 proton decays to oxygen 14. So looking at the 3 and 4 proton emitters, before I just showed one arrow giving you the exit channel, but now I'm sort of putting in how they decay. So the 2 4 proton emitters have the 2 steps here. I didn't show you the data for fluorine 13. It's a bit more difficult because if you remember, the peak sat on a huge background, so we can't say as much, but certainly it's clear that there's significant strength in fluorine 13 that passes through a couple of oxygen 12, the ground state and an excited state. And we can't rule out there is not some other component, but we can't say there is. So at the moment, it appears once you go past 1 and 2 proton emitters, you're decaying by some sequential steps of 1 and 2 proton decay. Okay, so can we go any further? So the next thing you ask, well, can we do 5 proton emitters? So I'm going to show you some evidence for 5 proton emitter in nitrogen 9. Notice nitrogen isotopes a little interesting because of the shape of the drip line. You have to go directly from the 1 proton emitters to 5. There's no 3 proton emitters in between. So how do we make nitrogen 9? So this is from the same experiment I've been showing a lot, the one with the oxygen 13 beam. And you knock out 4 nucleons. So in this case, there's 1 proton and 3 nucleons, 3 neutrons. So we look at now so it's a 6-body exochannel, so 5 protons plus an alpha. So it's just 1 extra proton than what you have in carbonate. And this is, so surprised how many events we got. This is the 5 proton plus alpha invariant mass spectrum. And again, it's with this huge 10 MeV. It doesn't make sense to consider this a wide resonance at all. So possibly there's some non-resonant background. Possibly there's contributions from very wide overlapping states. To try and at least isolate the low-lying states, if they're there, similar idea to back here, we were thinking, well, they presumably have some sort of sequential decay path. And the obvious one to look for would be a proton carbonate. Okay, remember carbonate ground state has a width of about 100 kV. And indeed, when you look at the mirror, there are a number of, even though there's a lot of consistency between experiments, they're always talking about neutron plus helium-8 resonances. So in a similar manner to looking for beryllium-6 in carbonate, to look for carbonate in nitrogen-9, you have to find a 4p plus alpha sub-event that reconstructs to carbon-8. So there are 5 ways of producing 4 protons from 5. So you find the invariant mass from all 5 such events. So now this is the decay energy spectrum of carbon-8. And very clearly, we have a peak here, which is at the right decay energy for the ground state of carbonate. And the peak has very little background, so you can gate on this peak. So you just demand that one of the 5 sub-events lie in here, and then that pretty much tags you as having a decay passing through the carbonate. So these red data points are the final spectrum we obtain. And you see we've lost most of the yield. That's not surprising. We're just presumably only the lowest lying states would decay this mode. And you also notice tends to suggest there are 2 peaks here. Though with the statistics, it's hard to really definitively say there's not one. So we look at the possibility that there's also 1 peak. So let's analyze these a bit more. So this is the same spectrum of the red data points I showed before. And we're going to analyze them in terms of a 1 peak fit and a 2 peak fit. So this is a wide state above the proton plus carbon-8 threshold, so it should be asymmetric in shape. So we use some R matrix line shape to fit this. So we assume this R matrix line shape for the P plus carbon-8. We then let the carbon-8 decay by 2 steps of 2 proton decay, incorporate the experimental resolution, and that's the fit I show here. And so it's this red curve. Actually, it's not a bad fit except for this data point, which is 3.6 sigma, I think, away from the fit. So it's not impossible, of course, at least just to have 1 data point so far away. But you can get much better fits, so the 2 peak fit is more likely. If you look at what we got for the peak parameters, so the proton plus carbon.
Sorry, Bob. Can you finish in 5 minutes?
Yeah.
Okay.
So this would be a, so the width is much larger than the decay energy. More than twice, in fact, the decay energy. And this really puts us in a region we call sub-threshold resonance, similar to a diproton. And so this puts this as more as a final state effect rather than a resonance. So if this is the true what's really happening, a single peak, we don't think there's a nitrogen-9 state. However, it's more likely that a 2 peak fit is the correct description. And actually the chi-squared, the value of chi-squared is very long. And partly that is we can't really constrain the widths of these 2 peaks. There's an anti-correlation associated with the width of 1 peak and the other. But we can define the decay energies of the 2 peaks quite well. If there are 2 peaks, what are they? So just based on the mirror helium-9, it's supposed to, at least experimentally, people are talking about a 1/2 minus resonance, and below that, maybe a neutron helium-8 virtual state associated with S1/2. So you could think, oh, this is the S1/2 strength, this is the 1/2 minus. And indeed, we asked our theoretical colleagues where these states would be, and this was with the gamma shell model, Josh Wiley and company, and they say the 1/2 minus is right here. So this gives us some confidence. This is correct. They don't find a 1/2 plus, and that's maybe not surprising because, as I said, it was a virtual state in the mirror nucleus, so it probably would be a subthreshold resonance, and that wouldn't show up. So if that's the case, this is not a real resonance, but this would be. We can't say experimentally because, as I said, we can't constrain the widths of these two states. So I'll just say that again. Is there a nitrogen 9 state? If there's a one peak solution, no, because that would all be S1R strength. It's just too wide for a real resonance. It's a final state effect. And if there's two, yes, then the upper peak is really correct. So this is the decay path. So this state here decays by proton, then to carbonate, and then you get the 2 steps of 2 proton decay. And if this is a real state, it also does the same. So have we reached the edge? That's what I want to talk about. So can we go another step, right? And remember these maximum width I talked about. So let's look at the magnesiums. Magnesium 18, this is experimental width. Sorry, 19, and then the next one, magnesium 18. This is experimental width. This is measured in GSI, we measured that. There was a 9 orders of magnitude change in going from 19 to 18. So if you want to go to magnesium 17, even if you go a couple of orders of magnitude well below, that would extrapolate well above 10 MeV. So ideally, you'd like to do this with some sort of theoretical structure, but I'm just sort of waving my hands at the moment. So I think it's unlikely. The neons, we don't know the width of neon 16. This is a prediction from Grigorenko. This is neon 15 measured at GSI. There was 3 orders of magnitude and going from here to here. We're already at 0.6 MeV. 1 order of magnitude would take us basically the limit I talked about. So unlikely, I think. And you can look at the oxygens and you can see going from oxygen 12 to oxygen 11. This is experimental measurement. This was, as I showed you, we didn't resolve the ground state, but this is based on the decomposition in theory. There was only 2 orders of magnitude here, but pretty close to 6. And if you believe VTEC, there should be more like 3, then it's probably unlikely. So I think we've pretty much reached the edge here. Obviously, not up here, there's some missing states and heavier things, but in these light nuclei, we've pretty much reached the edge. And you can ponder, are there other cases, or can you even get 6 proton emitters? The next case you might consider 5 proton emitters would be here. That's so far from the drip line. And I've already suggested that this case would, so that's, so where would it be? It's this one here, yeah. I've already suggested this doesn't exist, so I don't think this would exist. Probably the best case would be here. It's a little closer to the drip line. And if you want a 6 proton emitter, maybe here, this would be silicon 20. It's only 2 neutrons away. Maybe if we had some idea of the masses of this, it might help us get a better idea. Possibly there are better candidates at heavier systems. I haven't looked. So I'll summarize here. So we've been exploring the drip line, trying to go well past the, we've been exploring well past the proton drip line, trying to get to the edge. We've seen a lot of interesting things. There's a definite role for continuum and nuclear structure. As you get towards the edge of the drip line, you go to these more exotic cases, which undergo 3, 4, and 5 proton emitters. And more such emitters will undoubtedly be found, though I guess already we see in the 2 proton emitters up in like iron 45, they have trouble just getting to 2 proton emitters. So maybe it would be much harder to go further out and see these guys. And at least for the these very light nuclei, we think we've largely found the regime, the very edge of the chart of nuclides. And these are the collaborators in my associated with this work. Longtime collaborator was Xu Li, and we have a lot of the data with thesis experiments of our students. Higher experiments are done always in collaboration with Bill Lynch, Betty Sang, and now Kyle Brown's group at MSU, also in collaboration with Ellen Woosma. We have a very strong collaboration theory group here with Simon, Josh, and Vitek. And the Magnesium 18 was done in collaboration with Peking University. So I'll stop there.
Thank you very much, Bob.